All right, welcome everybody to week 10, day 2. We're going to be learning something today called call by pointer, which is the C way of doing call by reference. And you can use it in C++ too, and in fact, your next homework assignment uses it. I didn't write it. I wrote part of it, I wrote the homework, but the code that you're getting, I didn't write. And so it's actually going to be a great introduction to like how other people write code and stuff like that. So if I were to start off with something simple. Let's make a little void function here called add. We're going to have an int reference A, int B, int C, like this. And we said A is equal to B plus C. And down here we make a variable, int x is equal to 0. And we say add x, 10, and 20. What value is x going to have when I print it? So x is being passed in by reference to here, which means that the a here is being set. The a that's being set here is actually the x here, and then we print the value of x. So what value are we going to get when we print x? Does it matter that the variable here is named x and the variable here is named a? No. Yes, we are going to get 30. Very good. And a student asked earlier, like, does it matter like where the ampersand is? No. Compiles exactly the same way, no matter where you put it. So you get 30. Now, let me show you call by pointer. And this is going to be basically exactly the same. I'm just going to change a couple lines up here. And now we have what's called call by pointer. So learning point number 1, call by pointer is an alternative to call by reference. More or less does the same thing. And so what we have here is we are passing in the address of x, and I'll explain what the address of operator does in a second. But we're passing the address of x, and so here we have a pointer. We dereference the pointer, and it is going to set x to 30. So this code here, what I had up a second ago, is exactly the same code for all intents and purposes. It'll probably, I haven't checked, but it's probably actually going to compile to exactly the same assembly code even. Like there's literally no difference between this and that. It just depends which one you like stylistically better. This way is very common in C world. If you're a C programming, this is your only option. In fact, there is no call by reference. Bjarni added call by reference to C++, probably because people think that pointers are scary. And so instead of call by pointer, you have call by reference, which looks like that. You notice how the ampersand is here, whereas before it was here. That's why call by reference has an ampersand in it. Now, let's talk about this ampersand thingy here. So the ampersand is called the reference operator. It returns the memory address of a variable. That's what it does. And do you care what memory address? I mean, honestly, like, have you needed to know prior to this where inside of your computer's RAM X has been living? Have you needed to know this until now? What do you guys think? No, not really. If you're curious, I mean, you can print it. All right, let's print the memory address of X. And I will put down money. I won't actually, but I'll put down money that it's going to be near the top of RAM. The top of RAM is at 7FFFFFFFF, and I will bet dollars to donuts that we will get a number. Yep, there we go, 7FF, and then a bunch of numbers. Okay, so that is the location in RAM. That's like my street address that I'm at. That is the address that variable lives at. And what you're doing when you're passing it by reference or by pointer, it's the same thing. You pass in the memory address of a variable, and what the dereference operator, that's this guy right here, what the dereference operator does the dereference operator returns the variable at that memory address. Okay, so these two guys are opposites. Okay, so if you were to do something like print out the variable at the address of x, this is just going to print x. Okay, so print the variable at the address of x is x. So this is a very tedious and job security kind of way of just printing x. Okay. So what's going on here is it's saying set the variable at that memory address to be 30. And so you pass in the memory address of x, and then this is saying set the variable at that memory address to be 30, which is x. So x, this is like I said, x back in main is equal to 30. Okay, so if we were to look at our memory map, the way these things work is you have memory. Memory starts at 0, goes up to 7, F, 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 and up at the very top, you're going to have main somewhere, and somewhere within main, you're going to have x. Okay? And so what's happening is when you call that sum function, it's actually passing the address of x to sum, and then sum is going to read and write to this address. Okay? Now, one bit of interesting fun facts is down here is something I call the minefield of doom. And if you ever read or write to the minefield of doom, it will kill your program. The technical name for this is the 0 page. But I like minefield of doom better. So if you ever poke at it or touch it, if you ever read to it or write to it, the program knows you screwed up. The operating system knows you screwed up, and it kills your program. And so if we did something really bad, like let's try this. Okay, this doesn't compile because C++ is smart. So what this code here is saying is set the address of the variable to be 30. .30 is near the minefield of doom, incidentally, but that doesn't matter. By default, C++ will not allow you to convert between an integer and a memory address. These are not the same things. The value at that memory address of 7FFFFFF is 30. The value stored there is 30. But the address, its location, it's like I live at 1234 Main Street, but my name is Bill. Like these are two different things. And so by default, C++ will not allow you to store an int into an int pointer. But if you really wanted to, you can do it. And now, if you set the variable at memory address 30 to be 30, set the variable at memory address 30 to be 30, you're going to be hitting the minefield of doom. Okay? And well, let me just show you what happens. Boop. Segfault. Okay? Segfault. So, this is very, 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 very not good. Okay? So, probably should cast it like this, but whatever. Also, you can do it like this if you'd like to make it clear that A is an int star. In general, though, I put the star on the right-hand side. I'm not super 100% on it. But the reason why I do that is because if you do like int x, y, and z like this, you can see I put a star in front of the y. That means that x and z are integers. C is really weird. It allows you to declare integers and pointers to integers on the same line. And so these are actually two different types of variables we're making here. So we've made two integers named x and z, and we made one integer pointer named y. So an integer pointer is a variable that holds the memory address of an integer. And yeah, you can mix and match variables and pointers on the same line in C. This is kind of hazardous because what a lot of people do is they say, look, I'm making 3 integer pointers. I'm making 3 integer pointers named x, y, and z, and you're not. You're making one integer pointer named x, and you made a regular integer named y, and a regular integer named z. That's why I put my star on the right-hand side. It makes it more clear that x is a pointer and y and z are just regular integers. Okay. So, what if I did this? So I'm setting the variable and memory address 0 to be 0. What do you guys think is going to happen? Or we can set it to 9,000. What's your guess as to what's going to happen when we run this code? We are writing to memory address 0. Seg fault? Crash? Will crash? Let's find out. I'm going to guess it doesn't crash. See, it's fine. Everything's fine. Everything's fine. I don't know why you guys are... Wait. What if we turn off the optimizer? Let's turn off the optimizer and try that again, because the optimizer is on by default. Oh, there we go. There's the crash. So the optimizer, there's actually a rule that reading and writing to a null pointer is undefined behavior. And so the compiler detects that we're reading and writing to a null pointer, and it just deletes it. And so by having the optimizer on, it had the side effect of preventing our code from crashing, which is good, but actually not good. Because the first time you run your code without the optimizer on, your code seg faults. And that's not good. And so this is a case where having the optimizer actually will prevent you from crashing, but probably not in a good way, because you probably want to know you're seg faulting. So again, we were trying to read and write to memory address 0, and that's actually undefined behavior. The optimizer could remove it, because undefined behavior, you can do anything you want. You can just delete the line of code if it's undefined, or you can have it play the Macarena or by the Vander Holyfield Zeroff. It's all good. So with the optimizer off, though, it tried writing 9,000 to memory address 0, and we touched the minefield of doom. And it seg faulted. Okay. Now, you guys want to see something really horrible? Where was I? Okay. It is October. Yes, you are right. Okay, so pointers can have plus, minus, plus, minus, minus. What this does is point to the next x elements in the array they are in. So what if, let's just say what if I did this? So a++ means that the pointer that we had to some variable is now pointing to the next variable in the array. Is x in an array? Is x in an array? Or is it just a regular variable? It's a regular variable. And we're saying point to the next element in the array. So what's going to happen is that pointer that was pointing to memory address 7ffff, whatever, it's now going to be pointing to the next integer in the array. There is no other integer in the array. We're going to be reading and writing to random bits of RAM. Let's find out what happens. Might have your bank account information in there. Might have your phone number. Might be unused. In this case, we went off the top of the stack. So what happened here is the x probably was right at the very top of main, and we tried going up. And we actually exceeded the segment boundary that we're in. And it actually detected this, and we got a stack smashing attempt detected, and it killed our program, which is pretty cool. It's a cool name. It's an anti-hacking measure. What if we try going down instead? What if we try looking at the previous person in our array? What do you guys think? Seg fault? We're fine. What do you guys think is going to happen? Same result? Well, I mean, I don't know, because like the thing here is like when we tried going up to the next element, we actually walked out of bounds, you know, of the segment we're in. If we go down, I don't know. Let's find out. It works fine. But you can see that x was not actually changed, right? So here we printed out the value of x. We thought we were going to be storing 30 into x, but when we printed x, x is still 0. What happened? Well, we didn't actually write to x. We wrote to whatever variable is below x in RAM. What was there? Who knows? Hope it wasn't important. I don't know. We just changed something. Can you imagine how hard these bugs are to debug? They're immensely hard to debug. If you screw up anything with pointers, you can end up changing some variable somewhere that doesn't look like it ever gets changed, right? This is chaotic evil programming, exactly. So let's say we put a variable named Bob above it, who's equal to 666. We put a variable named Travis below it, whose variable value is 420. And we are going to see out, let's see here, see out Bob, X, and Travis. Why not? So we're going to output the address of Bob. We're going to print out the address of X. We'll print out the address of Travis. And we run it. Rabbis. Might need some other tab stops in here. There we go. It's all lined up. Okay, so here's the memory address of Bob. Here's the memory address of X. Here's the memory address of Travis. You can see that Bob is 4 bytes lower than X, and Travis is 4 bytes higher than X. Okay? So, we're probably modifying Bob, even though Bob never shows up anywhere within the code as being modified, right? So, we've got 3 completely regular integers here. We're calling this function, making it look like we're going to be writing to X, and actually Bob is changing instead of X. So let's just tablet here. So let's print the values of Bob. Probably need one more tab character. Print the value of X. And the value of Travis. And then we call that and do it again. Okay. So at the beginning, Bob is 666, X is 0, Travis is 420. After we call this add function, passing an X to it, it's actually writing to Bob instead. Bob is getting 30, and Travis is left unchanged. And if we were to change this code here to A++ instead, then you'll see that it is Travis that changes instead of Bob. So what do you guys think? You guys want to write code this way? It's great job security. Nobody will be able to fire you because nobody will be able to understand your code. So that's why a lot of people don't like messing with pointers, because you can do really horrible things in terms of like memory and things like that. Black Air Force coding. You feel confused? Okay, so what's happening here is that I'm passing in the memory address of X. And then when I say A++, that says, we have a pointer currently at X. I want you to point at the next thing in the array. There is no array. So it's just pointing at whatever's next to X in memory, back in main. And that just happens to be Travis. This is very much not good coding. This is never something you should do. This is absolutely garbage code, garbage tier coding. But it sort of demonstrates the value of like the plus plus operator, like not the value, but like definitely not demonstrating the value. It's demonstrating what it does. Okay. So, all right. So Havad, does that make sense? So A was originally pointing at X over here. When we said A++, it's now pointing at Travis. And that just happens to be because the compiler put Bob and X and Travis in order like that. You with me? Ta-da. Okay, so let's maybe make this not quite so stupid, and let's make it an actual array now. Okay, so let's do all this stuff here, and let's just make an array called R. Everybody say R. Yar, mateys. Okay, so this thing here means initialize the array to 0. This will zero fill the array for you, so you don't have to do it. Again, it's good practice to just always initialize your stuff. Otherwise, you will be sad when your code behaves differently. Okay. And we'll use iota again, just because it's fun. So we will iota from array to array plus 10, starting at 600. And so this is like saying array element 0 is equal to 600, array element 1 is equal to 601, array element 2 is equal to 602, etc. Okay, so iota fills a array or a vector with increasing numbers. It's just you could do it with a for loop. I just do it because it's amusing to me. And what we have here is the concept of a range. Okay, so a range is a pointer to where the algorithm should begin, and one past where the algorithm should end. Okay, so there's 10 elements in the array, from array 0 to array 9. Array 10 is one past the last element in the array. And so that's why you pass in a range like that. It's called the half-open range pattern, where you point to the first element you want the thing to work on, you point to one past the last element you want it to work on. And the reason why we do that is because that allows like these numbers to just kind of like, there's actually a lot of reasons why we do that, but you know, you can just put in the size of the array here and everything kind of works out. So if we want to do a range base for loop, this will work. Int x and r, cout x. And so there is our array, and it's been initialized nicely. And what if we did this? What if we did r and r plus 5? How many elements is this going to iota successfully, do you think? 4, 5, 6? You see, we've got a pair of pointers. And the first thing is going to be array 0, you know. Yeah, it's gonna iota the first 5 elements in the array, indices 0 to 4. It's just like in a range loop, or like a normal, not a range loop, a regular for loop. For int I equals 0, for int I equals 0, I is less than 5, I plus plus, it's less than 5, not equal to 5. Okay, so if we do this, then you will see that the first 5 elements get iotaed, and the remaining 5 are left at 0. You can do it the other way as well. So you'd say starting at array element 3, going up to, but not including, array element 6. So 0, 1, 2, 3, 4, and 5. So starting at element 3, going up to less than 6, 3, 4, 5. Okay. From 3 to 7, you guys understand? So any of these algorithms that take ranges, you have a start and an end, and that works with sort, it works with shuffle, it works with iota, it works with generate. All of these standard library functions, basically they all take a range. It says starting here, going to here, that's the chunk that we're going to work on. You guys understand? So let's make add a little bit more interesting now. Let's do this. Let's have it just add up all the elements in the array R. So for int I equals 0, I is less than something, I plus plus. 0, sum plus equals array square bracket I, turn sum. What should I put here? How big is the array? How does add know how big the array is? Can I call array.size? Does this work? No. This is why, students, we use vectors instead of arrays. You have, yeah, I should put a 10 here, but okay, I'll put a 10 here. And the code will actually work, right? So there you go. This is perfectly valid code. And I should probably scout the result. So scout sum add r. So you can see it has added up all the elements in the array correctly. But what if we do, I don't know, this? Now, what's the problem here? What's the problem? We got a problem. We are out of bounds. That is correct. So every time you change the size of your array in one place, you've got to like dig around and change it in another place. So typically what we do when we're working in the C world is we will pass in an integer for the size and do something like this. And constant size equals 10. Like that. You guys understand? And so anytime you will see arrays with C, there's only two ways that it can figure out how big the array is. One is by passing a size like this. The other is by having some element of the array be 0. And you have to guarantee that some element of the array is 0, and that's the end of the array. Okay? So it's not a great system. Use vectors instead. They're much better. And so if we do this, you will see that we now have correct code. Okay. You will see a lot of this in your upcoming homework assignment. Your upcoming homework assignment has a lot of pointers in it and a lot of arrays and things like that as well. So if you wish to take the homework assignment and refactor it to use vectors, you're more than welcome to. But you have to understand at least what's going on here so you can understand what's in the code, so you can understand enough to refactor it. All right. Now, let me show you something a little bit terrifying. It's not as terrifying as what I showed you. Actually, here. What if I passed in array plus 50? So whenever you have a plus with a pointer, and remember, an array is a pointer and a pointer is an array with a very small academic difference between the two of them. Because all an array is the pointer to the first element in the array. So if you ever have an array in C, like a C-style array like this, what it is you've got somewhere in memory, you've got R0 and you got R1, and they're all next to each other, and R itself is just pointing like right here. So all R is just a memory address. That's all it is. There's nothing special about an array. There's nothing special about a pointer. All they are is just an address in your RAM somewhere. And so when you're passing that array to a function, you're just passing the memory address of the first element in the array. And remember, if you do something like, say, array plus 1, well, that's pointing at R square bracket 1. It's pointing at R1. Okay? So anytime you add to a pointer, it just points to the next element. So if you add 1 to an array, it points to the next element in the array. If you add 2 to the array, then it's now pointing at array square bracket 2, and so on and so forth. So if you add 2 to R, then it's pointing at R2. You guys understand? That's, pluses, minuses, plus plus, minus minus. Now if I change R to 8, what will happen? Like, aha. Thank you. This needs to be set to size. Thank you. Okay. Good. So what is this going to do here? So I am passing the beginning point of the array that is being passed in is 50 to the right of my actual array. What do you guys think this code is going to do? It's out of bounds, but what do you think it's going to do? You think it's going to work? You think it's going to segfault? What's it going to do? Place your bets now. Place your bets now. Is it going to work? Or is it going to segfault? It worked. The sum that we got was 900 million. Did it work? I don't think so. I mean, it did what it said it's going to do. It added up the 10 values over there in RAM somewhere. It just read from some random RAM addresses and just added them up, and we get to know that their value is 900 million. I mean, there weren't random addresses, like in the sense of it being like a dice roll, but yeah, it just went 50 integers to the right over there and just added up 10 of them, and we got 900 million as the result. Yay! Use vectors instead. Okay. And we could do something like this, where, we could say array plus plus, and then the place where we're starting is going to be 1 to the right of where we thought we were going to start. There's all sorts of absolutely horrible, terrible things you can do. But what is on the screen right now is actually correct code. Okay? This is actually just fine. These would need to be updated. Array 3, array 4, array 5. Updated the comments. Okay. So, let me show you something more. So let's say integer pointer make array. And let's actually have it take a size, maybe. Size. Could be const, it doesn't really matter. Why not? Const. Okay, so int pointer r is equal to new int square bracket size. Return. Let's iota it. So since we're ioting up to element 7, I'm going to assert that the size is at least 8. Otherwise, this would segfault. And then I'm just going to return r. Okay, so what I'm going to do is, rather than doing this code here, I'm actually going to make the array in some function, and then it's going to return a pointer to the array that was allocated. And I don't like this, but it's done, and in fact, it's done in your homework assignment, so you have to get used to it. So, is this heap allocation or is this stack allocation? Why don't I put a delete? Because you have a new. You need to put a delete. Absolutely. Absolutely. We're actually not calling this code yet, so we actually don't need a delete yet. But we've got a new and we don't got a delete. This is bad. Okay. But yeah, first question, is this heap or stack allocation? This is heap allocated. So anytime you new memory, that memory is permanently allocated until the end of the program, unless you call delete. Okay, so I'm going to replace this code here. And what about this? Is this a heap or stack allocation? Here. What do you think? This is stack allocation. Okay, so I'm going to replace this little guy here and you with int pointer r is equal to make array passing in size. And so now what's happening is we call this function, it allocates memory, it returns the pointer back out, and then we can use it as an array. But there's one problem, our range-based for loop no longer works. And the reason why our range-based for loop no longer works is that we don't know how big it is. So we're actually going to have to replace this with a regular for loop, again, if we were using a vector, this would be fine. Okay, so I'm just going to replace this with a regular for loop. Equals 0, I is less than size, I plus plus. See out, array, square bracket I. Okay. Okay, so our code looks pretty good at this point. We're still missing something. Habafida said a second ago. But look, it's working. We allocated memory. We IO'd successfully. It's adding them all up. Everything is cool. But what is the thing that we forgot? What did we forget to do? What did we forget to do? We have a new. What's the rule of the Sith? For every new, there is a delete. Right? So what happened is we called new here. We returned a pointer. And at this point, we are now the owner of that memory. Again, a reason to use vectors, because vectors know when they own memory and take care of themselves. So don't let the variable vanish without deleting it. So it is our job to delete R. R needs to go away like this. Okay. So we call make array. It news memory and passes it back out in a pointer. We do stuff with it. And then when we're done with it, we delete it. And if we do this, oh, we didn't initialize the memory. Yeah, that was a change. All right. There we go. All right. Don't ever forget to initialize your values. It will be bad. Okay. So does this make sense to everybody? This is kind of the C way of doing arrays and stuff like that. You got news, you got deletes. It's like it's C++. But, you know, this emphasis on having pointers and passing pointers out and passing pointers to things is kind of the C style of C++. Modern C++ doesn't have a focus on pointers. You kind of got to know them, and ranges are used kind of everywhere. Kind of got to know them. But at the same time, like when I write code these days, I don't have any news or any deletes in my code, hardly ever. I rarely, I do use pointers, but I kind of rarely use them. There's some kind of cool stuff I'll do. Like I'll have a couple Pokemon loaded up, and I'll have a pointer for like who goes first and who goes second. And then I have the first one go first and the second one go second. And then I have the pointers switch who they're pointing at. And then you can go back and forth between who goes first, who goes second, just by like kind of manipulating a couple pointers. You don't have to copy things around and stuff like that. You can just have the pointer pointing at you're first, you're second. Okay, now you're first, you're second, stuff like that. And it's a very fast and actually kind of easy way of doing things like taking turns in a game and stuff like that. All right, so let's talk about your homework assignment. I think this is basically what you need to know. Do you guys understand what I mean by ownership? Like when you knew something, R is the owner of a block of memory. So when you knew something, this guy is responsible for deleting it. But if you return it, transfers ownership back out. Then you pass off ownership to somebody else, and it's now their job out in main to delete it. And tracking all of this kind of stuff is a complete pain. It really is. And so using a vector is vastly preferable to that of an array. Okay. But you will see all of this code all the time. It comes up. Okay. Like all this kind of code is a very common coding style. Not just if you're programming in C. There's a lot of people that do what we would call like C-like C++, probably more than do modern C++, for better or worse. So your homework assignment is going to be using Bridges Mountains. And what it is, let me show you what it looks like when you run it first. So when I run the thing, starting at row, I don't know, 300 something. Instead of having like an input test or whatever, instead what it gives you is a URL. So I'm going to go into Firefox, and I'm going to paste that URL here. And you can see, here we go, Mountain Pass, Colorado, starting row 300. I just typed in 300 here, right? And you can see what is happening here is that it is using topological height elevation data from the U.S. Geological Service. This is a chunk of Colorado using, I think, 1.5 kilometer square tiles. And what it's doing, it's starting at row 300. What it's doing is that it is moving to the right and moving to the right and moving to the right, starting at column 0, going all the way to the last column, moving to the right, moving to the right, moving to the right. And at each move, what it's doing is picking between the 3 tiles to the right. There's east, northeast, and southeast. It's picking the tile that has the closest elevation to the current tile. So let me sketch this out for you. So let's say you've got a big old 2D array. It's not a very square array, is it? Yeah, I got a little 2D array here. And we're going to start on row 1, column 0. Our elevation here is 90. And to the right, we've got 80, we've got 110, and we've got 130. What you do for this assignment, all of the code to do file IO is done for you. All the thing that loads the topographical data is done for you. What you have to do is the user will type in, I want to start on row 1. Okay. You always start on column 0 because you always start on the left side of the map. You're going to be traveling all the way to the right side of the map. Okay. Isn't it the other way around? What is the other way around? So what you need to do is figure out which one of these 3 spots is closest in elevation to the current one. Your goal is to always travel to the east. Your goal is to always travel to the east, minimizing the change in elevation that you make. So which one of these 3 spots should we move to if we are trying to minimize how much elevation change we have in our step to the right? Good. Also, all of you guys got this one. We're going to move here. Okay. So we start here, move here, and then let's just make up some numbers. 75, 90. So if you're on the top row, you have to be careful. A lot of students segfault because they actually go out of bounds. They actually try reading off of row -1 and segfault. So be careful for that for the homework assignment. But we're here. Which way should we move? Should we move east or should we move southeast? We got 2 options. We can move east to 75. We move southeast to 90. East is correct, so we should move this way. And then let's say we have a 300 and a 200. Which way should we move? That is correct. We should move southeast. And for this assignment, what you do actually every time you make a move like that is you actually set the height value there to be -1. So each one of these tiles is going to have a height of like -1 set on them. And then what happens is that's how it knows to draw the path here. Each one of those purple tiles is a tile that I set to have a elevation of -1. And then when the thing draws any -1 elevation, it draws in purple. Okay. So Bridges is a tool that allows you to visualize the results of your code. You could print all of these values to screen, but it's hard to actually grasp with the human mind when you've got just a giant 500 by 500 array full of elevation values. Okay. So at every point along the way, it is trying to minimize the change in elevation. And you'll see these things will sit there and kind of like run along a canyon for a while. And, see how it's like running along the mountain line here until it gets stuck and then it kind of runs up a crease. So it's not a shortest path algorithm in the sense of like Dijkstra's or something like that you learn in CSI 26, but it is a greedy algorithm where you just step to the right, step to the right, step to the right. You guys have a week to do this, and you can work on it with partners if you like as well. The website is going to be UNCC Bridges .github.io.com, or not .com, but bridgesuncc.github.io. You can watch a little video here introducing Bridges to you all. What you're going to do is, and let me show you what Bridges is. So like Bridges allows you to like visualize the results of your computations, and it's all interactive. So this is the result of like somebody's program, right? And I think it's doing like a Bacon number or something like that. Yeah, here it is, Bacon number. And so what it is, it's tracing how far some actor is away from Kevin Bacon. If you've heard of the 6 degrees of Kevin Bacon thing. So it's tracing from Kevin Bacon here, Kevin Bacon to Morgan Freeman. And so Morgan Freeman is 1, 2, 3, 4 actors away. So okay. Maybe 5, whatever one that is. Okay. And go back. All these things you can kind of mouse over and click and drag on. What you have to do for this is you have to go up to login and you have to create an account here. And then after you create your account, you're going to go to profile. And the profile will show you your username and your API key. Your API key is like your password. And you might be like, oh, wow, I have the professor's password. Yeah, but I'm about to click on generate new API key and invalidate it. Okay. So copy your username, copy your API key onto the server, and let me generate a new API key now. There we go. Now if I try running the code here again, watch what happens. API key invalid. You see that? And the memory leaked as well. But you see that? My API key, I just invalidated a second ago, so now I can't log in using my saved API key. It's like your password, okay? So what you're going to do is cd bridges 40. What you're going to do is you're going to open up main.cc, and you're going to type in your username there, right? Like if I was you guys, I'd type in W. Kearney, and my API key was whatever it was, I don't remember anymore. But you'd paste that in, right? Then once you do that, delete this line here, okay? So by default, when you try compiling your code will not compile, and it will tell you you need to register on Bridges first. So don't try and do any development until you are registered on the Bridges website, okay? So in order to get your code to compile, you have to delete this line of code, okay? That's just there as a reminder to not try and do any development until you've registered already, okay? And if you try compiling the code without using the makefile, if you try like using compile to compile it, then that won't compile either, and it will tell you to use make to compile the project. So in order to compile the project, you have to type make. And it takes a while to compile. Okay, well, not in this case, because it's touch. So it takes a while for this code to compile. Okay. So just be ready for that. You can do this project in your groups from last time. It's going to be set up as a group project. If any of your partners have vanished or anything like that, message me and I will put you guys into new groups. Yeah, by default, this is a group project as well. If you look, there you go. It takes a while, right? So if you look through the code, you can find places where it says like U:. And if you know how to search for this, by the way, in Vim, you type /U:, hit return, and then you can hit N for next, N for next, N for next, N for next, and this shows you all the places in the code where you need to be writing code. Okay, these are the parts where you have to do something. So some of these things are pretty easy. For example, you need to change the title to have all of the last names of the people in your group in it. Okay. I'm not going to tell you how to do it, but it's somewhere within here. You have to change something deeply mysterious in order to put your name in it. Okay. Another thing you have to do is you have to change the color so that the line being drawn is not purple, but blue. And that will be somewhere in here. All right. So the color right now is purple. It's magenta. It's 100% red, 100% blue. Colors, by the way, range from 0 to 255. And this is the red. This is the green. This is the blue. So 100% red, 0% green, 100% blue is purple. Okay. Or magenta. So it's your task to change this somehow to be blue. All right, change the line color to be blue. I'm not going to do it for you. You just have to use your knowledge, your secret knowledge of numbers and color theory to make this purple turn into a blue. Are you guys up for the challenge? There is also, I think, a crashing bug somewhere around here as well. I can tell you where that one is, though. Do you guys understand colors? Red, green, blue, ranging from 0 to 255. So 255, 255, 255 is white. 0, 0, 0, black. 0, 255, 0 is pure green. You guys understand colors? Is that cool for you? Okay. That's another letter grade. So the hard thing here is the find path algorithm. And so if we look at what they give us, there's a couple functions here. You can notice that they like call by pointer, right? Which is why that's the topic of our lecture today. They like call by pointer. They could have done this as call by reference because this is C++, but they chose to use call by pointer instead. So it's passing an image width, image height, image max value, and file name. File name probably should be passed in by const reference, but who cares? And it is returning a array of data. You're probably the owner for. Okay. And one of the nice things about call by pointer is that you can see here which variables are going to get changed by the function and which are not. Right? So we're passing in the address of width because width is going to be filled in. What this function does is it opens the file for you. All the file stuff is done. You don't have to do any file stuff. It opens the file, it reads the width, it reads the height of the map, it puts them into those two variables there, and then it loads all the data into an array, and it keeps track of which element is the highest element in the map, and then it returns a pointer to that chunk of data that it just loaded from the file. And so one of the nice things about call by pointer is you can see which of these parameters are being modified by the function. In C++, from main, call by value and call by reference look exactly the same, right? You can't actually tell with call by value and call by reference, if you're just passing width in, you actually don't know if width is changing or constant or whatever. With call by pointer, you can look at this and be like, all right, the first three values are going to be written into, the fourth value is not. And that's kind of a nice thing about call by pointer style. Okay. It's not enough for me to use it, but I can at least appreciate it. You know, like you can look at it and be like, all right, those first three parameters, they're changing. They're going to be changed by read data. Okay. So come back up to the top. You can see this is a array being passed in. These are just 3 pointers to integers. And you might be like, but wait, a pointer to an integer and a pointer to an array look exactly the same. And yeah, they do. It's not good because you don't know, right? Like if this is pointing to one thing or if it's pointing to a lot of things. And this is, to me, one of the fatal weaknesses in the C programming language is that the pointers don't give you any clue as to if you own the memory or not, if you're responsible for deleting it or not, and it doesn't tell you how many elements are at that memory address. And there have been a lot of hacks, a lot of crashes and bugs over the years because, you know, somebody changes the size of an array in one place, but forgets to change it in another, and you get buffer overflows or underflows and things like that. So it is not my preferred coding style. Okay, so get image is going to, I think this one's done for you actually. Let's search for that. Yeah, this function is done for you, and so you just have to change the color from purple to blue for where the line is, and so the actual main is pretty much done, I think. So you just have to put in your name and API key and delete this line here. Then main. So this creates what's called a bridges object. The bridges object is what behind the scenes it's sending data to the bridges website and causing those nice visualizations to happen. So this is already done for you. You don't have to touch it. Read data is done for you. You don't have to touch it. The title you have to change. Whatever. It's easy. We then ask for the starting row. And then find path is the algorithm you have to write. This is the heart of the program, find path. Get image is done for you. And then this right here, where you do the bridges.visualize, that connects to the bridges server, uploads all of your data to that, and then it creates a new project on the bridges website. And I'm using a project ID of 1001. Let's not listen to Gojira right now. So if we go to bridges unc.github.io and we log in. So again, we have our username, we have our API key, but the project number, you can actually pick any project number you want. It doesn't really matter. But the project number is like a save slot. So if we come over here, you can see that you know, project number 1001 is this one, project number 901 is this one, project 990 is this one. So if you want to like have a separate slot in the save database, however you want to put it, give it a different project number, and then you can keep your previous ones around. So you can see here, this is the result of a earlier computation I did. And I just changed the project ID so that it wouldn't override it. Basically, every time I run this code, it will keep overriding whatever's in slot 1001. Okay. And then this thing here, bridges, set data structure to the color grid, and visualize. That does all the heavy lifting for you. It connects to a server, it uploads the data, it tells it what to draw. The only big issues that I had with their code was that they're returning an owning pointer, right? Like right here, this is returning a pointer that you are now responsible for deleting, and they weren't deleting it. So I added in a couple of lines here. This also is returning an owning pointer that you're responsible for, and it wasn't deleting it. So I added this in and that. Read data is done for you. I don't think you need to touch it at all. Get image is done for you other than the color. That's real easy. So find path is where you're going to do your work. So you're going to have a starting row. You're going to start at column 0, and you're going to grab the elevation of that row, and then you're going to look at the elevations to the northeast, east, and southeast, and pick the elevation closest to your current one, you move there and rinse and repeat, setting the elevation to -1 every time you move on. And if you're like, but how do I get the height elevation from a array or whatever, this is how you do it. Or what I'd recommend, honestly, is rather than using all these pointers and arrays and stuff, let me show you what I did. I rewrote it, okay? Let me make sure I don't show too much. I'm gonna hide the screen here. Let me just show you a little bit of this. So what I did was I had the data, I changed everything. So there's no pointers, there's no news, there's no deletes, there's no any of that, really, at least for the elevation data. I changed it into a vector of vectors. So I made a 2D vector, essentially, out of it. And what that allows me to do is just not have to worry about any of the stupidity involving pointers and things like that. So you are more than welcome to completely rewrite the code as long as you get the right result. Okay. So the goal of this assignment is to teach you about pointers, call by pointer. The goal of the assignment is also to show you how people code that aren't me. There's a lot of different ways that people do C++ development out there in the real world, and most of them aren't me. And so there are different coding conventions and things that people use and techniques they use and things like that. And it's good for you to be exposed to them. Kind of like eating your broccoli is good for you. You know, like you might be like, oh, I'm not used to pointers and stuff like that. But like a lot of code out there is written this way, you know, and so it's good for you to like be able to read it and understand it and maybe just change all of it because you don't want to deal with it. But even still, you have to understand it before you can change it and replace the arrays with vectors and things like that. Do you guys understand? It's a learning experience. It's school. But it's not just for school. This is how a lot of, you know, industries do their coding. Yeah. Kind of. You're not convinced. If you like go to work for like Ford or something like that, like they use pointers all the time. You know, what's a vector? Never heard of that. Refactoring it is so you can eat cauliflower rather than broccoli. So either way, you'll learn something. You'll either learn something by learning how to do it the, you know, C-style C++ way with like pointers and call by pointer and stuff like that, or you get experience by converting it into modern C++. Both approaches are valid. Both approaches are things that I've done professionally in the real world. Okay? Either way, it's good for you. So that's our class for today, and I will see you guys on Friday. Peace out.